Okay, let's start. Hello, everyone. My name is Ajay Jacob, and I am the Director of Projects at the California Dreams Hub. I'm also Director at the Information Sciences Institute at USC. Today, I have the pleasure of welcoming Professor Robert W. Heath, Jr. He is the Charles Lee Powell Chair in Wireless Communication in the Department of ECE at UC San Diego. He is the recipient or co-recipient of several awards, including the 2019 IEEE Kyo Tomiyasu Award, 2020 North Carolina State University Innovator Award, 2021 IEEE Vehicular Technology Society James Evans Avant-Garde Award, so many awards. And he has also authored several books. I mean, as an example, Introduction to Wireless Digital Communication. He is a licensed amateur radio operator, registered professional engineer in Texas, a private pilot, a fellow of the National Academy of Inventors, fellow of the IEEE, so many other fellows as well. And he's also elected to the US National Academy of Engineering. So today I have the pleasure of welcoming Professor Robert Heath to give a talk on embracing reconfigurable antennas in the tri-hybrid MIMO architecture for 6G. Robert, the stage is yours.
All right, thank you, Ajay, for the nice introduction there. You did a good job of keeping it brief. So I'm happy to be here to talk about a topic that I think is really instrumental for 6G or possibly 7G, depending on your perspectives here. And so this is work we've been doing in my group about the last year and a half with Professor Rodrigo Castellanos from UT Knoxville, Professor Chunbyung Che from Yonsei, Seung Yang, one of Professor Che's students, and two of my graduate students at UCSD, Joey Carlson and Nitish Deshpande. Both Joey and Nitish will be graduating in 2026. So if you like this work and you're looking to hire, they may be open to discussion. So just a little bit of background here. So I was at the University of Texas at Austin for almost 20 years. I spent 3.5 years at NC State, and now I've landed at UC San Diego. I'm hoping that this is my final destination. I think I'm the only person that's really who moved to Raleigh and actually has come back to California. And after seeing the housing prices, I realized why no one goes the other direction. So I'm going to be talking to you today about MIMO communications. I mean, I've been working in the area of MIMO since essentially my PhD. So, we're approaching 25 years at this point. And so I've been there since the early days. And I keep trying to look for other research topics, but I just have always really stayed true to the multiple antenna communications and have been looking at MIMO since the before 2000. And so this is a snapshot of how MIMO communication systems, so MIMO, we're talking about multiple transmit, multiple receive antennas, and how they've been scaling in the last 25 years since the early inception in WiMAX and 802.11, and then in 4G, and now up to 5G here. And what you can see on the x-axis I have is just the date, and then I have on the y-axis the single user MIMO configuration, just to give you a sense of how the dimensions are growing, number of transmit by number of receive antennas. And then you can also see, that the dimensions, generally speaking, have been growing, right? So Wi-Fi started off with 2x2 MIMO, then it was 4x4, and now even up to 16x8 configurations. And 5G stagnated a little bit, though it seems like it's potentially going to be growing even further for 6G if we look at the trends here. And so my talk is really about looking at an approach for continuing to scale up the MIMO dimensions as we go into 6G and beyond. So the starting point, when I put this talk together, I went back to a talk I was giving in 2014, and I updated the slide a little bit here, but it's more or less copied from that talk there. And in 2014, that was around when we were starting to look at millimeter wave as potential 5G technology. So I was at UT Austin. My colleague Ted Rappaport had been, um, I think, had just moved to NYU, but in 2012 he was working with Samsung. They were doing the first measurements to validate this idea that millimeter wave could be a viable technology for cellular systems. And so I got excited about millimeter wave as well. And what really interested me was essentially the following observation here that, when you go up to the higher carrier frequencies, the antenna shrinks, the aperture shrinks. And so everyone says, oh, this millimeter wave, there's, it's really high path loss, but it's really just you're using a little antenna. And so if you want to keep the aperture fixed, the story is that, well, aside from using a really big directional antenna, you can also use an antenna array. And the ray gain from that antenna array overcomes the loss of the shrinking antenna size. So in the same amount of area as a lower frequency system, you just tile a bunch of higher frequency small antennas, coordinate them together, and then you don't have that path loss effect anymore. Now, the other thing that happens when you go to millimeter wave, aside from the antennas getting smaller, is that the bandwidth is getting bigger. And the bandwidth gets bigger because, well, that's the whole reason to go to millimeter wave, is to have higher bandwidth channels to get higher data rates. But when you go to higher bandwidth, your power is not increasing, transmit power is not increasing, but the noise power is increasing. So you also need some extra gain to overcome the effects of the larger bandwidth. And you can achieve that also using an antenna array. So if you have an antenna array, the transmitter and receiver, you get enough array gain to overcome this diminishing aperture effect by keeping the aperture fixed, and also to provide additional gain to overcome the larger noise power. And what we found in these early days of studying multiple antennas for millimeter wave is that the way that we were using multiple antennas at that time was primarily as a digital architecture. So those 2x2, 4x4 MIMO systems, every antenna had its own RF chain, its own mixed signal component, and all the beamforming combining, everything was being done in a DSP. The problem is when you scale up the antennas by a factor of 10 and the bandwidth by a factor of 10, the power consumption also goes up. The data converters consume more power, the RF consumes more power. So this architecture didn't seem to scale to hundreds of antennas in the configurations that might be of interest for 5G. And so then the next part of the story was well, what can you do? So one of the approaches that we were working on and published a paper on this with collaborators at Samsung is on this hybrid architecture where the beamforming is split between analog and digital, in a sense going back to the way that beamforming used to be done in the 60s, 70s, and 80s, which is primarily in the realm of analog. And so we were proposing to split the analog and the digital so that there's a few digital dimensions and there's digital beamforming coupled to many more antennas, like maybe 100 antennas and 10 connected to 10 digital dimensions. And by doing this, you reduce the number of complete chains that you need, the amount of digital signal processing that's required, and also the number of DACs or ADCs in the system there. And so it becomes possible to reduce the power consumption, which is especially valuable for those higher bandwidth systems here. And so we got very excited about this because this changed the way MIMO was being done for those of us like me working in signal processing communications. And it introduced some new interesting hardware constraints, and it really changed a lot about the algorithms that we were developing in MIMO. And so this opened the door for millimeter wave to become like a new, interesting, and different signal processing problem. Now, of course, I'm talking to a lot of people who've actually built these devices, and you know that, of course, all I really did was trade the challenge that I had in the digital signal processing and push it back over the fence to everyone working in analog. But I view that as also creating a set of opportunities. But I acknowledge that it wasn't like it created a whole bunch more problems versus maybe the one or two that it solved. So that was the story back in, when we were looking at millimeter wave at the beginning of 5G. And so now we're looking at, interesting technologies for 6G. It's about a decade later. And we have a similar story now. There's a lot of interest in going to the FR3 bands, then the upper mid band, 7 to 16 gigahertz, to get access to higher bandwidth channels. And you have the same scaling effect as before. The antenna shrinks, so you need more antennas to maintain the same aperture size. But you also have this extra effect that there's interest by the carriers to not have to densify the network. The millimeter wave, one of the biggest drawbacks of millimeter wave is that to get good performance, you also needed to densify even more than at lower frequencies, which made it the infrastructure cost very high. So if we want to go to the centimeter wave band, FR3, but we want to keep the same infrastructure, we need additional gain to overcome these effects here. And so you can get that additional gain, of course, from using antenna arrays and potentially even larger arrays than at the lower frequency systems here. And the problem is that when you scale up the hybrid architecture from, say, hundreds of antennas to thousands, the power consumption creeps back up, and it also seems to be become less feasible to have 4,000 antennas in the hybrid architecture. And so then this led us to the question of so what can be done? And as a MIMO person, I want to see that the MIMO technology keeps scaling, so I can be in business another 20 or 30 years. So the idea that we decided to exploit was to go back and look in electromagnetics, and we have to revisit this concept of reconfigurable antennas. And so reconfigurable antennas, I mean, it's been around for at least several decades here. And it's a mechanism by which it's possible to change the characteristics of the antenna itself. So as opposed to beamforming, where the signals being sent to several antennas are being adjusted, here the antenna properties itself are being adapted. For example, by adjusting an RF switch or changing a capacitance value, or maybe physically moving the antenna, or having a microelectronic machine to turn off and on a piece of an antenna, or even changing the material properties that antenna is made from here. And the thing that's really interesting about reconfigurable antennas is that it becomes a way to get effectively a larger aperture with potentially reduced power consumption, because many of these approaches for reconfiguring the antenna are actually lower power than if you were driving a bunch of antennas as part of an array. And so that's what got us interested in this area here. And so you can think about the role of reconfigurable antennas at play. So ideally, we would like to be able to create, an arbitrary distribution of current, right? I mean, that's really what's happening with an adaptive antenna, is you're just creating a particular distribution here. And then doing that digitally, so we drive each antenna with a separate signal and adjust all the signals to create desired response or pattern. The hybrid array, this is a subarray example. Some of that beamforming is done in digital, some of it's done in analog. So we introduce additional analog components like splitters and phase shifters. And then with a reconfigurable antenna structure, what we're imagining is that on top of the hybrid structure, we can reconfigure the antenna elements themselves. And so maybe each reconfigurable antenna has an aperture roughly the same size as the maybe like a 10 element array. And so we can get essentially, we think we can get about a factor of 10 from antenna reconfigurability, on top of the benefits already of the hybrid architecture. And this can be used to expand the aperture and take the system up from hundreds of antennas to thousands. And this is what we call the tri-hybrid architecture. So there's three layers of precoding at the transmitter and receiver. So there's a digital precoding or beamforming, an analog beamforming, and there's also an electromagnetic beamforming component where the antenna properties in some form are also adapted. And with one of the designs that we've looked at, we can get about a factor of 10 in terms of increased antennas, and then the power consumption, it is also quite a bit lower because the power consumption of reconfiguring the antenna itself is very low versus other architectures here. Now, of course, you can do simulations of different, very specific designs and come up with many, many kinds of trade-offs. And that's an interesting topic to explore exactly the places where reconfigurable antennas make sense, exactly how much power consumption one is saving, and what are the other potential benefits and drawbacks. And so that's some of the work that we've been starting to address, and I'll tell you a little bit about this in the rest of the presentation. So the rest of the presentation is divided up into three sections. So first, I'm going to talk a little bit about just the types of antenna reconfigurability that have been studied recently. Most of this work is outside of my group, and I'm just essentially refreshing your knowledge about this and giving you some ideas where the the people working like myself in communications and signal processing are looking for reconfigurable antenna ideas. Then I'll talk about some of the ways that we see the antennas being put together as part of the hybrid architecture. And then I'll give it a final example with dynamic metasurface antennas, and we'll look at some performance trade-offs in terms of spectral efficiency and energy efficiency. So reconfigurable antennas been around for a long time. There's a lot of ways to reconfigure an antenna. Perhaps the one that's has been the most common is approaches for changing the frequency response. Multi-band antennas have been used quite extensively. There's other ways though to reconfigure an antenna. They can be reconfigured to create and direct the pattern. They can also be even reconfigured to change the polarization. What I'm going to be focusing on is essentially gain pattern reconfiguration, although polarization reconfiguration could be thought of in through the same lens. And I'm not going to look too much at frequency reconfiguration and other reconfiguration methods because I'm mostly interested in the reconfigurable antennas for getting more aperture. So some of the approaches that have been proposed in the literature, one of the ones that we like is the dynamic metasurface antenna. And this is essentially a leaky wave antenna where each of the slots can be digitally controlled by changing the bias of a reactor or by switching on and off like a pin diode. And by changing that, you change the resonant properties of that atom, and then that affects effectively a phase shift on the signal that comes out, a phase shift and an attenuation. And then by coordinating them together, it becomes possible to beamform across a whole bunch of slots. And you can see some examples here where the beamforming has been like attempts have been made to create like a DFT type code book, a set of using this metasurface antenna instead of phased array. And there's some benefits. You get some reasonable directivity with this metasurface, but you also, the side lobe properties tend to be not as good. And so there's benefits and drawbacks of using reconfigurable antennas. And I will be talking much more about the metasurface antenna later. So I will defer more of that discussion to the later sections. This is one of the approaches, a metasurface antenna, but there's a lot more. So what's happening in the communications society, I've seen the last year or so, a whole bunch of new papers on related to stacked intelligent metasurfaces. And a stacked intelligent metasurface, from my point of view, I'm still trying to understand exactly, trying to look at it and understand exactly its benefits here. But it's essentially a set of metasurface. They're stacked together. So layers that are placed in front of a set of antennas. So it's a bit like a lens, but each of the properties of these layers are controlled. So instead of it being like a reflective surface, like in intelligent reflective surfaces, it's a transmissive surface. And the properties of the transmissive surface are being changed to affect, better beamforming capability. I'm still trying to understand exactly what this is. It's definitely a type of a reconfigurable antenna, but I don't have a great understanding yet of the benefits and drawbacks. But you can see that it seems to be possible that using a SIM it's possible to get better beamforming than you could achieve with just the single array. And so it's a way of also approximating, creating that very flexible current distribution that we would ideally like to achieve. So that's the way I think about the SIM. And this is a topic that a lot of the folks in my community are starting to look at. Most of the papers are more analytical. I haven't seen as many actually building it yet. Another design is this parasitic arrays. We've been looking at this a bit in my group, although I won't tell you too much about it today. But here is where you can um, adapt um, the RF parasitics by changing the loading of the parasitics to create, for example, um, you by changing the characteristics of the parasitic, you can direct the beam pattern um, and so it's another way to adapt the beam. And it is we have found that actually from a mathematical point of view, there's a lot of relationship between the parasitic arrays and the metasurface antennas in some sense. So parasitic arrays, you're controlling the parasitic elements, and then the performance is obtained by adapting them in the right way. But having like many parasitics actually doesn't work very well because the coupling effects, they decrease. So parasitic arrays are a way of getting a bit more aperture, but maybe not hundreds of wavelengths, but maybe, another wavelength of aperture, two wavelengths. So there's a lot more, reconfigurable antenna designs. I mean, there's thousands of papers on reconfigurable antennas. So here's another one. It's like fluid based, where there's literally a liquid fluid, like mercury, for example, that moves around in the substrate. It moves around. And then there's electrowetting on device where little droplets can be controlled and moved. So these are liquid antenna-based approaches. Um, and so I think I showed this already here, effectively each of these different designs has its own set of trade-offs, its own ability to direct the pattern, to get gain, its own set of trade-offs between the how it's designed, how much bandwidth it can support, the power consumption. So in a sense, it's very nice because it opens the door for many possible types of reconfigurable antennas to be integrated. And it also makes it hard to come up with like one holistic framework for putting everything together, which I think is interesting research direction. Okay, so that was just a little bit of background on reconfigurable antennas. So now I move to talk some about how we see these being integrated together as part of a MIMO or hybrid MIMO architecture. So a little bit of background here. I don't go through too much of the math, but just to explain that the hybrid architecture, the analog and the digital beamforming are split together, are split. And one of the challenges from a signal processing perspective with the hybrid architecture is that however you configure the analog components, that becomes part of the effective channel that's measured by the receiver. And so doing even basic communication engineering tasks like channel estimation become greatly complicated by the hybrid architecture. And this is in part what led to the beam-based structure that 5G uses to configure MIMO. There's a two-stage procedure. There's which involves a coarse transmission over the SSB beams, and then involves a second transmission of refinements over CSI ports, and then a feedback, and then a final transmission. So that the way that 5G has been designed from a MIMO point of view has been to support a hybrid kind of an architecture. And so some of the ways that we see, reconfigurable antennas, I mean, we can just plug them into the hybrid architecture itself. We could, and just make each antenna reconfigurable. So if I have 200 element hybrid array, I attach each of those to a reconfigurable, 200 reconfigurable antennas, and as a way of trying to expand the aperture a bit. And so now, and then you see now a third layer of reconfigurability, the digital, the analog, and the antenna. And That's not the only thing we can do though. We could actually, just if we don't need a huge aperture, we could just replace maybe the analog subarray with a reconfigurable antenna itself. And so here, the selling point is that perhaps we can get similar beamforming performance, but with lower power consumption by replacing the analog signal processing and antennas with just one reconfigurable antenna. This is a way of, reducing power, but without it's reducing power, but without. Sorry, let me go back here. What's happened here? Yeah, reducing power and not going after the aperture there. Now, there's a lot of different considerations here. So in the hybrid architecture, in the early work that we did, we were always imagining a fully connected network where the input ports from the digital, every input could connect to every possible output here. So there was, a whole lot of splitters, combiners, phase shifters together there. Actually a lot of losses associated with making such a complicated network. And so most of the hybrid examples that we see in industry are all based on a subarray architecture, where the subarray, every digital output here goes into its own analog processor and influences only a subset of the antennas. So you need essentially just a set of parallel beamformers instead of a single very complicated beamforming network. So we have a similar set of considerations also with reconfigurable antennas, because there's many kinds of reconfigurable antennas. There's some that act like a single antenna. There's an RF port in, and there's control lines, and they just change the characteristics of the antenna, like that metasurface antenna I shipped. But there's also some that have multiple inputs and controls. Like the stacked intelligent metasurface, there were multiple antennas that were radiating into the metasurface itself. And so there's single port and multi-port, and there's different trade-offs with the different designs. And so one of the things that I found, particularly, interesting about this is that, it requires like developing, algorithms, looking at analysis that is a little more specific. So instead of just, drawing like a generic triangle like we do in most of my papers, now we can say, okay, we're going to consider this specific kind of antenna, this specific kind of reconfigurability, and maybe look at simulations and in HFSS and ADS and try to integrate everything better together from a system perspective. And this has also driven some of the work that we do in my group on physically consistent information theory, where we're trying to do theory that better matches the physical considerations and the circuit implications of realistic antennas and components. But in short, all of these trade-offs here with the configurations, the types of antennas, it makes for a wealth of, possible papers to write, possible designs to explore. And so I think it is a very rich area for doing research. And the tri-hybrid architecture, it adds essentially this new dimension here. So it makes the configuration of the hybrid links much more challenging, because now, like the channel that's measured is a function of both the analog configuration and the antenna configuration. And so this may require supporting tri-hybrid MIMO, it may need yet a different architecture for 6G. So instead of beam-based MIMO and 5G, maybe it needs something else to allow both the antennas and the analog to be configured together. It's really unclear to me at this point, and maybe 6G is the development's already started, and maybe it's too late to put reconfigurable antennas in, and maybe it will impact 7G. But I remain optimistic that it will still play a role here in 6G. And so from a pre-coding point of view, again, I won't go through all of the math here in detail, but I wanted to highlight a little bit of like how this changes many of the problems that we looked at before, like in my group related to hybrid pre-coding. So we were usually considering like an analog precoder. So it's a matrix with a set of phase shifts that comes from maybe every phase shift is finite because you're driving it with certain resolution. And so then the pre-coding problem was, well, let's find an analog configuration, a digital configuration, somehow that maximizes rate. But then the tricky part is now, like if the antenna becomes part of the pre-coding, we have a third layer in the middle there. So we've got like an antenna pre-coding, an analog pre-coding, and a digital. And each of these could be frequency selective. We usually treat the analog part as frequency flat, unless you're doing like true time delay beamforming. But in the usual work, we're considering it frequency flat. And the digital pre-coding can be frequency selective. But some of those designs I showed you of the reconfigurable antennas, they're actually also kind of frequency selective. So you may need to account for the frequency selectivity in the antenna and also in the digital together. So that makes it actually the problem becomes much harder. Even just characterizing the set of possible patterns that can be achieved with different configurations can be really, really challenging because there's many ways to configure and to do that without just doing an extensive amount of, electromagnetic simulations is another potential challenge. Even more is like radiated power. When you change the antenna configurations, different amounts of power can come out. And normally we're normally assuming that there's perfect matching and all the power applied to the antenna in the hybrid case comes out. So now we have even more constraints that, we want to look at radiated power and so it does really change a lot of the signal processing, the configuration aspects of doing MIMO communications. And so now I'm going to wrap up in this last section here with just a little bit of a design example with dynamic metasurface antennas. And by design, I mean more from a signal processing design perspective. So this is another picture of a metasurface antenna with that slotted waveguide. You can see the slots, you can see the adjustments to create the directed beam pattern here. In the work that we do, we usually use a circuit model to characterize each of the slots. And so we use prior work to understand the sets of patterns that we configure with the metasurface antenna. We have also built such an antenna in my group. We've been working with Professor Imani at Arizona State. We're going to be testing that out later. So I do want to point out we're not just, using simplistic models of the antennas. We are using relatively realistic models that we simulate, and then we're also now trying to build and validate some of the ideas. Unfortunately, we haven't actually tested the antenna that has been returned yet, so I don't have any good results. Hopefully it will work. More than likely, we'll have to fix it and remake it again, but you know that story. So some of the things, like from a beamforming point of view, if you have a metasurface antenna, I like to think about the metasurface antenna like a hose, a water hose with some holes in it. So the energy tends to leak out, more the earlier holes rather than the later ones, right? Um, because the signal is propagating through a waveguide, there's also an effect of the waveguide that attenuates and phase shifts the signal as it propagates through. And that has to be accounted for in the beamforming in itself. And then the thing is that how the fields look in the waveguide depends exactly on how each of the slots is tuned. And so, because you have this this example, the sinusoidal effect, but when you change the different varactor diodes, you change a bit how this looks here. So the ideal pre-coding, even if we just have one of these metasurface antennas, forget the analog, forget the tri-hybrid, just one reconfigurable antenna. Even that is actually not quite trivial to do from an array processing perspective to configure it. Some of the other challenges include, we like to think of these slots as phase shifters, but they're not phase shifters. They're actually resonators, and they're resonating. They're basically filters. And so you can't actually turn a slot off, and you can't get all of the phase shifts that you might want to get even out of a slot. And so from a signal processing point of view, we usually think of each slot as, instead of being an ideal phase shifter where you can get any phase, the phase and amplitude are coupled together. And there's even a set of weights you can't even achieve. And this whole circle, it keeps decreasing and decreasing. All of these have to be accounted for just to design beamforming weights just for a single metasurface antenna. So for comparisons, what we did in this simple study was we looked at a hybrid architecture with subarrays where we've got power dividers, phase shifters, and then we looked at the case where we add the metasurface antenna on top of that. So we're going to compare a hybrid with static antennas to a hybrid with reconfigurable antennas. And I'm assuming all the numbers are dividing so that everything, works out well. The number of slots in the metasurface antenna is kind of like the effective number of antennas that it supports here. So in this example here, this metasurface antenna has 5 slots, so it's acting kind of like 5 antennas. And then we have, three, so 5 slots, 3 analog chains, and being driven by one from the digital here. And then I want to just mention briefly a little bit of the challenge again of doing all of this here. So from a spectral efficiency point of view, like the usual approach we took in the hybrid architecture papers was we assumed that the receiver was fully digital. So we were just going to focus on configuring the analog and digital precoding together. And so here, like if I just focus on configuring just the analog digital are part of the hybrid, plus also the weights of the DMA now. So now I've got to put all of them together. I put them in the spectral efficiency perspective equation, and I've got a radiated power constraint, and then I've got a constraint that the analog beamformers have to be realizable from the analog phase shifters, and then the DMA has to be configured within the space of possible DMA precoders here. This is a very hard problem to solve because we have all of these complicated constraints. So even in the hybrid case, it's actually not solvable exactly. So we approximate the solution by using a good approach we've developed for the hybrid case, and then we try to find a metasurface solution that tries to map that together. So we solve for a higher dimension MIMO problem, and then try to factor that into a solution that incorporates the metasurface antenna. That's the approach that we took just to generate the solutions here. But there's a lot of work that can be done from a mathematical point of view here. And then we did also quite a bit in terms of accounting for trying to add up the power consumed from the local oscillators, the PAs, the mixed signal data converters, the phase shifters. I'm sure that everyone will like to comment further and criticize this model here, but this was our starting point. There's more details in the paper that I mentioned here. And then one of the things that's been a little bit challenging with this work is that the usual precoding work, we have a power constraint, but that power constraint is really the norm of a matrix or a vector. It's not like really radiated power, but with isotropic antennas and under some assumptions, you can kind of pretend those two are the same, but not with the reconfigurable antennas. And in particular, that some of the antenna configurations, they don't radiate well. So you have a power constraint, but you're not even close to that constraint. And then working with radiated power where you're integrating around the antennas is kind of hard from the signal processing optimization framework. So we end up actually fixing the power that goes into the hybrid subarrays instead of trying to fix the power that comes out. And so then when we do the comparisons on my x-axis is always going to be input power, not radiated power because of this. And I can explain more about this later, but it's also described well in the paper. And so in the end, we're going to compute configurations of antennas and compute the spectral efficiency. And we're also going to compare with energy efficiency where we divide that spectral efficiency by the consumed power. And this makes sense because we understand that using a reconfigurable antenna, there are some drawbacks versus having a fully digital solution. So we expect that the performance from a rate perspective may not be as good, but when we factor in consumed power, it should hopefully be better. Otherwise, there's no point to the tri-hybrid architecture, which is of course fine too. And then this is the main performance result I'll show you here. So the plot on the left is a plot that you would see in a lot of my papers on hybrid precoding and a lot of other people as well, where usually the x-axis is is like either transmitted power or SNR. Here as I mentioned, I'm plotting input power. And then this is spectral efficiency. So in the usual MIMO kind of a paper, you see curves that look like this here, and the slope of the curves is the spatial multiplexing gain of the system here. And we see this is the fully digital approach. This is fully connected hybrid, partially connected hybrid. And then where we've added the metasurface antennas, and this is metasurface antenna only here. And so we've added the metasurface antennas on top of the hybrid. So, we would hope that it would be like a lot better. But because we've been accounting for very carefully the sundry losses, it's not quite as good. But then when we divide by the actual consumed power, we can see that the the metasurface approach, the DMA approach has the best efficiency, but because there's not any phase shift, there's not any hybrid architecture, but it also has the worst rate performance. And so we see that the DMA, the tri-hybrid approach, has a pretty good balance being energy efficient and also giving performance that comes close to the fully connected hybrid solution, but having much more energy efficiency. So basically, for the same amount of power, one can use the tri-hybrid architecture and get a better um, performance when we account for the consumed power, not just the power used for transmission. And then I will just mention here that while I was just giving you this example with metasurface antennas, and you may or may not like metasurface antennas. We have been extending this to other types of reconfigurable antennas. We've looked at parasitic antennas and also a certain type of liquid antenna, and we have reported in this paper that has been accepted some results where we can show the places where like using a liquid antenna on top of the tri-hybrid architecture also actually works well, and it has other some other advantages from the metasurface antenna. But really, to do this, you really need to understand the antennas very well, all of the losses, because if you neglect the losses, all of the reconfigurable antenna approaches, they look too good. So we're really trying to account for everything, correctly here, that the best that we can. Okay, so I have a couple of minutes left, and I'll just share with you some final thoughts. First is that in the like communication society, there are two competing areas with the tri-hybrid architecture. One is called liquid antennas, and another one is movable antennas. And each of these have developers and proponents of the particular architectures here. The liquid fluid antenna arrays is inspired by the liquid antennas I showed you, but it is really like another name for like a reconfigurable antenna, in my opinion. And the movable antenna arrays, they are literally looking at arrays where the antennas can be like turned off and on or actually manually shifted around. And there's many papers on both of these topics now, probably hundreds of papers that describe MIMO communication with liquid or movable antennas. And, from my point of view, these are just types of reconfigurable antennas, and we should try to think about them as part of the tri-hybrid MIMO framework, because a solution that I develop for a metasurface antenna can potentially be modified to work with a liquid antenna, fluid antenna, movable antenna, if we can find the right mathematical framework to describe how to configure it. And of course, I think it makes sense. Like if we want to see these in 6G, I don't imagine that we want to design 6G for a liquid antenna or a metasurface antenna. We want to design it for general reconfigurability. So we need to abstract what are the key ingredients of antenna reconfiguration that should be used for standardization purposes. Like we're not going to standardize the antenna, but we can standardize how to adapt, or what are the control lines, what are the control mechanisms. And then, just to conclude, so yeah, I'm really excited about the tri-hybrid MIMO architecture. I've had the opportunity to work with my students have taken courses with people in circuits and antennas, both at NC State and at UC San Diego. So that's really helped me to grow my research program, having the opportunities to have my students understand these areas better. So I'm also looking at how to reconfigure these tri-hybrid architectures. We have another line of work involving machine learning, which is something we've been doing in my group about 10 years now, configuring MIMO links using machine learning. And of course, you can do that with a tri-hybrid architecture. It makes a lot of sense. There's a lot of stuff that's hard to simulate, hard to predict. Model-based methods are tough. And I've got some other work as well. And so since I've been relocated to UC San Diego, I'm looking to build new partnerships, looking for new sponsors that want to work on this next generation of MIMO. I've also been excited to be part of some proposals where we're looking at incorporating aerial vehicles. As a pilot, I like the flying stuff I find is really cool, detecting and tracking aerial vehicles, communicating with such vehicles. And I've got a couple new research directions as well. One that's related to low complexity LLMs, and another one I'm really excited about in quantum error mitigation. So I'd be happy to discuss these opportunities more, and feel free to reach out after the talk. And with that, I think I will stop here, and I think we have the time for questions.
Yes, thank you, Robert. I mean, this was such an insightful and futuristic research that you're doing, and thank you so much for this great presentation. Let's open it up. There is one set of question that is being asked from Taimur Islam. Taimur, you could come up and ask the question to Robert, or do you want me to read it? Okay, let me read it. The first question is, why not add more antennas to analog chains than having separate reflective surfaces, especially if they are collocated?
Yeah, I haven't looked at anything at reflective surfaces, so I'm not really sure how to address that. I think maybe this results because sometimes when people see metasurface, they think intelligent reflective surface. But I'm not looking at that at all. Like I'm looking at actual reconfigurable antennas, not reflective surfaces that are on a building somewhere or even a reflect array. I haven't looked at that at all.
The next question is if the risk can be thought of just adding more antennas to the analog chains in the hybrid architecture to control the phase. So how does this become the third dimension?
Well, this comes back to the connection between this work and risk. So if you had a reflect array, like a parabolic antenna where you have the reflector and then you have the illuminator like very close together, that could be thought of as like a reconfigurable antenna. But the usual way that people are thinking about RIS is the reconfigurable surface is far from the transmit antennas. It creates another reflector in the environment. And then from my point of view, well, I think that someone could write a paper on RIS plus the trihybrid MIMO. To me, that's not part of the trihybrid MIMO because that's in the environment. And if it's part of how you're engineering a reconfigurable antenna, then yes, it is fair game, and it's another way of designing a reconfigurable antenna. But we have not looked at reflect arrays in that way.
Thank you. Is there any other questions? Oh, there is a third question. Oh, a couple of questions are coming. Yes. So what frequency range do you see the most promising? 5G FR2 failed because millimeter wave is not a known line of sight technology, and for mobile users that is crucial. Will your work extend to lower frequency of FR3 about 7 gigahertz, or is it mostly done at 24 gigahertz?
I mean, what I mean, the reconfigurable antennas, I think are most interesting for below 30 gigahertz. So many of the designs that I've cited, like the metasurface antennas, are usually they've been used for like SATCOM, like 15 gigahertz, 12. But I think FR3 is the sweet spot for this technology because FR3 is where we've got just to go from 3 to 15 gigahertz, you need a larger aperture, but the base station, the intersight distance has to stay the same. So you need an even larger aperture to get to deal with the bandwidth, the intersight distance, and also it maybe you don't have as much scaling on the devices. So I think FR3 is the sweet spot for basically centimeter wave is the sweet spot for this technology, and um, it's certainly valuable for lower frequencies, but I haven't I don't know I just think I think it's more interesting in that region.
Thank you, Robert. So CY Sung is asking, has the DMA metasurface rad hard capability or concern?
I think I didn't quite get all of that question there.
The question is the metasurface rad hard concern, or is it enhances the capability for the rad hard?
I'm sorry, I don't know what rad hard.
Radiation hardness is what he was asking. So is it
Yeah,
rad hard, radiation hardened antennas?
I'm not sure what that is.
Okay, that's fine. There's another question. What is the expected impact on NF when a tri-hybrid architecture is used at the receive side?
So NF, I guess, is near field or noise figure.
I think this is impact on near field. Oh, near noise figure. Noise. What is the expected impact on noise figure when a tri-hybrid architecture is used at the receive side? Yes.
Yeah, yeah. I think it will have an impact. We haven't looked at what that impact would be, but because the antenna reconfigurability shows up before the LNA, so you would it would naturally have some impact, but I haven't looked at that on my group.
Okay. Another question from Amin Khalil. Would not reconfigurability be more effective at the middle between TX and RX, which is the reflecting surface, than it is at the TX side?
Yeah, I'm not a huge fan of the, intelligent reflective surfaces. I mean, I just don't I don't think that there's a huge appetite for people to deploy such surfaces on buildings when you can just put another base station there and you can wirelessly backhaul it. So I just don't see too much interest on my side in reflective surfaces. And that's why I think actually it makes more sense to try to have more reconfigurability at the base station or at the user than to try to reconfigure the environment.
Hmm. So Edwin is asking another question. How does the concept of holographic MIMO compare to the tri-hybrid MIMO architecture?
Yeah, it's a good question. I've been having this discussion with several folks, and the problem is that the tri-hype the holographic MIMO has been co-opted by different groups to mean different things. So holographic MIMO to some people is like the ability to create a arbitrary current sheet. So there's some work on that. And then other people, holographic MIMO is kind of the sim. And then so it means other people, holographic MIMO is like MIMO in the near field. So it means many different things. To me, holographic MIMO is really just very large MIMO system. And I think that the tri-hybrid architecture I think you could consider it to be holographic MIMO if you want. I don't use the term holographic MIMO because I've seen it used in too many different ways to be consistent. But I think we could in the if we think of holographic MIMO as extremely large, very flexible MIMO systems, then I think that the tri-hybrid is the way to realize that, in fact, is mainly the only way.
Hmm. So CY Sung asked about the rad hard question, and he's asking that is this metasurface antennas flyable in orbits?
Oh, I see. Yeah, that's a good question. I think there's people that work on these designs much more than me that can answer that. I mean, my group isn't, we're barely building one antenna just to be in the lab. So I don't know. I don't want to speculate if they're good enough to fly around yet.
I have a question, Robert. So what is the realistic distance? We talk about millimeter wave as well as the terahertz regime. I mean, when it comes to 6G and 7G. So what's the realistic distance here before the noise factorials actually degrades the
You mean in terms of like FR3 or what do you mean?
FR3, the realistic distance for before the noise figures can be kicked in?
I mean, in most cellular systems, they're, yeah, I mean, usually interference limited. So
Correct. That's the reason why I was asking, because you have so many number of antennas, and then the interference can actually create havoc, right? I mean, bring in a lot of noise. That's the reason I asked. Yeah.
yeah, but this is great because, the one of the best ways to deal with interference is not, it's not successive interference cancellation, really just beamforming. I mean, so beamforming, either at the transmit or receive, is a very robust way of managing interference, right? I mean, down tilt in a cellular system is basically a way of just beamforming the signal down to reduce out of cell interference. That's a very coarse approach. We have some other work where we're looking at beamforming to null satellites, so you can share spectrum with satellites. And again, that's empowered by having a large array and enough degrees of freedom to direct where the energy is going. So I think that it is, and that's another reason actually that the array should be larger here in FR3, is because of the incumbents that are in a lot of the spectrum, and you get extra degrees of freedom to manage the spectrum as a secondary user more effectively.
Hmm. As a follow-on question would be that when it comes to this heterogeneous integrations, when advanced packaging, do you foresee any, do you foresee this, do you foresee any packaging advance going to make these structures better behave from a noise perspective or from a link budget trade-off?
I mean, I think the packaging is hugely important. I mean, the packaging, honestly, from the places I usually present my work in the Communications Society, Signal Processing Society. I mean, no one talks about a package, uh, to be clear. Um, but when I used to work more and worked a bit in automotive radar some years ago, and it turned out that the radome on the millimeter wave radars was hugely important, and it was affecting a lot the performance. And there was this trade-off between the designers who wanted, to put the radar inside the grill and the performance. And so the packaging is very, very important. I don't have any insights on packaging, but what I can say is that the approach that we're taking, where we are using electromagnetic tools to simulate the antennas, can also work with packaging too. And so I think that framework is going to allow us to develop techniques and algorithms where the antenna and the package is studied and thought of as together, which in my community is like, everyone, just the antenna for everyone is just a triangle on a stick. So we're moving in that direction, but I don't have any insights, but I think we're going to be able to understand it better with this physically consistent approach.
Okay. Thank you, Robert. Thank you once again for this insightful talk and also for all the answers to the questions that was asked. Now, let's get into the next week. We will have Boris Weisband from UC Irvine giving us a talk on packaging. So thank you all for attending this seminar, and have a nice evening.
All right. Thanks, everyone.
Yeah,
Bye.
thank you, Robert.